Hi, can you hear me?
Yes, sir.
Okay. So I think the official IOQM scores have been made available. I saw somebody post on the website. Did you get a chance to check that?
Yes, sir.
Okay. Yeah, we still don't know the cutoff, but at least we know the scores.
Oh, okay.
Okay, I think we can start. So I hope you got a chance to go through the problem set I posted on Friday. So as usual, I try to have the first few problems easy and the next one bit challenging. So we start with the easy ones. Okay, so anybody who has solved question one? So in case you are not solved, let me motivate you with some smaller, like simpler problems of the same type so that you get an idea of how you are supposed to approach a problem like this. Instead of just revealing the solution, let us work towards the solution through smaller examples. So to begin with, we can have, for example, and the original question was 3 types of objects and 8 distinct boxes. So let us first understand what is the kind of question this is. So in a way, so this is obviously a combinatorics question, but there can be so many ways to look at the same problem, and they fall into some typical buckets, like for example, like distributing objects into boxes and those kinds of things. So in particular, the way you can think about this problem is that so there are 3 types of flavors, right? So 3 flavors and 8 objects, and each object will not flavors, three types of objects. Yeah, actually I got mixed up because originally I had put them as ice cream flavors, but anyway, 3 types, doesn't matter whether it's ice cream or objects. So 8 objects, and each object will have one of the 3 possible types. So if you think about it, you can represent this as a function, right? Because you can have the first set of 8 objects, right? 1, 2, 3, 4, 5, 6, 7, 8. And each object will get assigned some particular type. So if I represent the types as, let's say, type 0, 1, and 2. Okay. So then each object can be assigned a particular type. So in a way, we are talking about a function, right? The function which goes from the first set to the other set, right? And the condition is that each object has to be each type has to be represented at least twice, right? So each element of the second set has to have at least 2 elements of the first set which map to that, right? So for every element of B, there exist at least 2 elements of the first set, such that both the objects are given the same type. Okay. So in terms of this representation, can you think of a simpler problem which is comparable to this kind of problem? Yes, Raghav.
So I think what we can do is like we can consider three types to be like the number of boxes in the three types assigned be x0, x1, and x2.
Okay.
The sum would be 8, and each x1, x and each x0, x1, x2 has to be greater than or equal to 2.
Right. That is one way to look at it, but only thing is there, the objects are distinct. So when we formulate a problem in that way, right, we don't make any idea about which object is assigned to which type. So if let's say these are 8 identical objects, then I was solving that equation is the way you would do it, right? So
Okay.
yeah, so if with the only change that instead of 8 distinct objects, if 8 identical objects are there, then that is sufficient to solve the problem. Otherwise, what we'll have to do, for examexample, as you said, let's say x0, x1, and x2 is equal to 8. For every solution we get, let's say 1, 3, and 4. So this means that 4 objects are going to be choosing type 2. Now to account for the distinctness, we have to then actually count like how many ways are there to distribute the 8 objects into these 4 categories.
Sure. So can't we just multiply by 8 factorial?
No, the thing is ordering. So, for example, within this 4 objects which are choosing type 2, the order doesn't matter, right? So, if 1, 2, 3, 4 are both all choosing second type versus 4, 3, 2, 1, but they are still in the same bucket. So, the order within the type doesn't matter. So, it is not just about arranging them on a straight line, right?
No, I don't get it.
So, why are you saying 8 factorial?
Because like we are going to have 8 objects and then we can arrange them in 8 factorial ways since they are distinct.
Yeah, we can arrange them in 8 factorial ways. And now your idea is that out of those 8 let's say we arrange them as A, B, C, D, E, F, G, H. And your idea is that if let's say we are looking at distribution 1, 3, 4, then the first object will go to type 0, next 3 objects will go to type 3, and the last 4 will go to type 2, sorry. Something like this?
Yes.
So the difficulty here is the EFGS. Just look at the last 4. If I just rearrange them as something else, HGF. So then still the object assignment is still the same. These are all still of type 2. But if I just count them as 8 factorial permutations, I will be separately counting this case and this case.
Okay, sir, I got it.
So then, I mean, the real way to do it is that out of 8 objects, it will have to be 8 choose 1 to choose whichever object is going to go into the first type. Multiplied by 7 choose 3 into 4 choose 4.
Okay.
Right? And then I have to sum it up over all possible. So 1, 3, 4 was just one example. In general, it will be like IJK. So sum over all such possible IJK. That will be the answer.
Okay.
Right? So I mean, computing that sum can be quite difficult to do it that way. But there is one more way to look at this problem, and there is. So do we know that we can classify functions as 1, 1 or 2, those kind of things, injective and surjective functions? Are you aware of these concepts? So for example, if a set A and set B is there, and a function f. So when do we say f is 1, 1 and f is onto? Are you aware of these terms, everybody?
Yes. So 1, 1 is basically injective function. When
Yes.
all elements in A, we have a corresponding element for B.
Correct. So 1, 1 is that if we have 2 elements, for any 2 elements A1 and A2 in the first set, their images will not be identical. Correct? This is 1, 1. And what about onto? Onto is what we call surjective.
Surjective function.
So what is the condition for onto? So onto means that basically every element of the second set has to be represented. So for every element of the second set, at least one element of the first set should get mapped to that object. There could be more than one, but at least one has to map. Okay, that is what we call surjective. Okay, so a function which is both injective and surjective, that is what we call a bijection. So bijection is basically perfect one-to-one mapping between every element of the first set and every element of the second set. So now, I mean, as I said, I want to motivate, instead of directly giving the answer to this original question, let us try to solve this easier problem, that if I give you 2 sets of size, let's say n and k, okay. So there is a set A which has n elements, and another set B which has k elements. and we are looking at all functions going from first set to the other set. So the first question is, how many such functions are there? I mean, even before adding any conditions, how many such functions can be there? Okay, so this is the starting point before even we try to solve a harder problem. So if you are not able to answer this question, then we have to ask an even simpler question. What is a function? What do you mean by a function? What is the definition of a function? Yes, Anushka.
It's a mapping from the first set to the second set.
A mapping from the first set to the second set. Yeah, that is a fine way to look at it. And is there any condition that what kind of mapping it has to be? Or it can be anyhow we want?
Such that if we have a function, if we plug in the value of a, it should give us plug in the value of any element in a, it should give us an element in b.
Yes, correct. So there is a way to write the same idea in a mathematical language, and that is basically we look at the cross product of a and b, or sorry, what we call Cartesian product of a and b. Okay, so Cartesian product of a and b. Do you know what that is?
So I think if we have a as a set of elements, say 1, 2, 3, 4, b is a, b, c, d, then the Cartesian product will be 1a, 1b, 1c, 1d, 2a, 2b, 2c.
Right. Basically, you take our ordered pairs where the first element comes from set A and second element comes from set B, right? So A cross B is all such ordered pairs. So it is a pair and the order matters such that A comes from the first set and B comes from the second set. So if let's say the first set, if you know the number of elements in the first set as M and the second set as N, how many elements will the Cartesian product have?
M into n.
M into n, right? Because basically every element of the first set and every element of the second set will get combined, right? I mean, very simple example, if suppose A is 1, 2, 3 and B is 1, 2, 3, 4, then all the pairs like 1, 1, 1, 2, etc. all the way to 3, 4. So all the 12 pairs will be formed. So this is what we call the Cartesian product of two sets. Okay. Now we can define the function in terms of the Cartesian product. So a function is a subset of the Cartesian product, such that, so can you think of what conditions this subset has to satisfy? So basically the idea is that a subset of element a comma b will belong to our function f, if and only if. So we are defining the function in terms of these pairs of elements, that if f of a is b, then instead of writing it that way, I can write that a and b, this pair belongs to f. So as you said, Anushka, that every element of a has to have some output in terms of your mapping, right? So therefore, what should happen is that for every element of a, there has to exist a b such that a comma b belongs to it, right? This will ensure that any value you pick from the first set, there will be at least one element in that Cartesian product which is represented in our function. And not only that, there has to be unique. So this exclamation mark means unique. So there exists a unique element of B such that a comma b belongs to f. Okay, I hope everybody understands the definition. We can illustrate that with a picture. So the picture is that, let's say the set A has 1, 2, 3, 4 elements and B has 3 elements. So as we said, the Cartesian product has all 12 possible combinations. But suppose it were the case that first element maps to 1, let's say, third element maps to 2, fourth element maps to 3, and 2 does not map to anything at all. So this will not be a function, right? So every element of A has to be represented. So 2 has to map to some object. So for example, suppose 2 also maps to 1. Okay. So then you see our function f will be comprised of these pairs, right? 1, 1, 2, 1, 3, 2, and 4, 3. So this represents all the possible pairs of A and B such that f of A is equal to B. Okay. So this is the definition of the function that we can use. And see, the important condition is that I think we get sort of assume that the function has to be nicely behaved. That okay, we are standard function like x plus 1, x minus 1, x square. These are nice functions. But in the pure definition of a function, there is no guarantee that it has to be nice. You can define it anyhow you want, as long as every element of A is assigned a unique element of B. And just as I said, maybe if 2 did not map to any element, then it will not be a function. Conversely, suppose some element map more than one. So let's say 4 maps to 3 and 4 also maps to 2. So this is not allowed, right? Then how we define f of 4 is ambiguous. So therefore, this f of whatever set you have, it cannot have 4, 3 and 4, 2 both. So I mean 4 has to appear exactly once, but it has to appear. Okay. So I hope this definition of the function is clear with the example. And so now going back to the problem, let's suppose now take this case only. Let's say so here set A has 4 elements, set B has 3 elements. So can you tell me how many such functions can there exist?
I have a doubt first.
Yes.
Sir, over here we have mapped 2 elements of A to B. Yes, think it's not valid, but when we have fx is equal to x square, that happens, right?
Fx equal to x square is correct. So the thing is, there can be 2 objects in B where both objects of A belong to the map to the same element. That is allowed. This is allowed. This is not allowed. So if I mean obviously, for example, here also the first set is larger than the second set. So there will be some 2 elements of the first set which will be forced to map to the same element of the second set, right? So that is allowed. But see, there is no ambiguity. Even if 2 elements belong, so let's say like what you say x squared. So minus 2 gets mapped to 4 and 2 also gets mapped to 4. But the function is f of x is x squared. Still, there is no ambiguity that f of 2 minus 2 is also 4 and f of 2 is also 4. So there is no problem with that. But if this picture happens where one element is being assigned to 2 values, let's say one is being mapped to 2 and one is also being mapped to 3, then you cannot write the value of f of 1 without ambiguity, right?
Sir, so basically f of x is equal to root x is not a valid function.
F of x equal to root x. So the thing is, this is a confusion which school textbooks create, because when they write the symbol root x, it seems to indicate that this can be plus 2 as well as minus 2, but the sort of technical right way to write is that so given an element, given some, let's say, positive element, okay, y is a square root. Okay, see, important word, I'm not saying it is the square root. Y is a square root of x if y square is equal to x. So under this definition, root 2 let's say 2 and minus 2 are both square roots of 4. We cannot say 2 is the square root of 4 because 4 can have multiple square roots. So both 2 and minus 2 are both square roots of 4. But when we write root of 4, this does not mean square root of 4. The technical name of this is called radical of 4. And the radical is always supposed to indicate to the positive value. Okay. So radical is always the positive square root. Okay. So therefore, in this way, f of x equal to root x is a function, because the use of this symbol means that we are talking about the positive square root. Okay. But if I just say f of x is a square root, is any number which is a square root of x, then it will not be a function, because then the possibility is that f of 4 is equal to 2 and f of 4 is also equal to minus 2. So then this will not be valid. Okay. So yeah, I mean, this is I would have liked to cover this in a separate topic, but because you brought it up, it's good to clarify this. Okay, so understand the difference between a square root which does not guarantee uniqueness, and the radical. When I say the radical, there has to be only one positive square root.
Also, sir,
Okay.
I had one more doubt. When you have written the definition of function,
Yes.
you've written the function is a set of subset of A cross B. A comma B is a subset of F. So F is
No. Yeah. So actually, I wrote this separately. Let me write it in a more cleaner way. So function F. So when I say the function F is a subset of B, so the function itself is the subset of A cross B, such that for any element small a of the first set, there exists a unique element B of the second set, such that this particular ordered pair A comma B belongs to F. Okay. So if this part is clear, let us think of this question, that suppose first set A has 4 elements and set B has 3 elements, then how many functions can we form from A to B?
12.
12. Why?
Yes, sir, because the mod of the number of elements in A into B would be 12, and the function is a subset. So the maximum number of elements it can have is 12, right?
Yeah, but F is a subset of that set, right? So
Yeah.
I mean, your A cross B is itself a set of size 12. And then you are considering all possible subsets of that set.
Okay.
if you- A cross B is 12 and F is a subset of A cross B.
Okay.
So then how many possible such subsets can you create from a given set?
So it will be, I guess, 12 choose 1 plus 12, or 12 choose 2 so on after 12 choose like that. Or 12 choose.
Do you know another answer? Actually, that is not the right answer, but let's just stay on that point. So you are saying it is 12 choose 1 plus 12 choose 2 plus up to 12 choose 12. Something like that. Yeah. So because I guess what you're thinking is that if you consider all subset of size 1, that will be 12 choose 1. All subsets of size 2 is 12 choose 2. And all subsets of size 12 are 12 choose 12. And you are adding them all, correct?
Yeah.
Is there another way to count all the subsets of a given set? In general, any set S of, let's say, n elements, how many subsets of S can be formed?
So 2 to the n, right?
2 raised to n, right? And that is also equal to n choose 0 plus n choose 1 plus up to n choose n. So this is a standard formula. I hope everybody knows this by binomial expansion, or anyhow you want to look at it. So you can count the subsets of S as you did, Anushka. That let's count all the subsets of size 0, size 1, all the way up to size n, and add it up. We'll get all the subsets of S. Alternatively, you can look at it this way. I want to create a subset. Your S has n elements. Let's say the elements are 1, 2, 3 up to n. For each element, you can ask a question whether or not I want to include that element in my set, right? There are either I'll include one or I will not include one. So there are two possibilities for the first element, two possibilities for the second element. So each element is giving you two possibilities. Either you include that element or you don't include that element. And these are AND questions, right? The first, we have to answer the question for the first element and the second and the third. So the answer is simply the product of all of this, which is 2:1. Okay, does that make sense?
I didn't get the second part.
This choosing the subset way.
Yeah.
I will take a small example. Let's say we choose a very small set of, let's say, 8 elements or 3 elements. Let's say your set S has 3 elements, 1, 2, and 3. Okay. Now, in your approach, what would we do? That we are counting all the sets, all the subsets, right? Including the empty set is also variable subset. Okay. So therefore, the answer will be 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3. Correct? as
Yes.
per the first method which you are understanding. Now the second method which I am saying that, let's say I want to create a subset of S. Okay. So A will have some of the elements of S. So your S had three elements, 1, 2, 3. So how can I create this set A? Either I will pick the first element or I won't pick it, right? So one is either in my set or it is not in my set. So whether or not to choose one is a yes no question. And that yes no question has two possible answers.
Okay.
Right?
But
For the second element, again I have a yes no question. Do I want 2 or not? Again, two possible answers. Same for 3. Do I want 3 or not? Two possible answers. So 2, 2, 2. There are totally 8 possible ways to answer all these yes no questions. And each combination will give me a different set, right?
yeah, correct.
So this is like basic multiplication principle, that there are 2 ways to do the first task, 2 ways to do the second task, and 2 ways to do the third task. So the total number of ways to do all the 3 tasks is 8.
Got it.
Yeah. So as per that, your answer of how many such functions will be there. Your A cross B had 12 elements. So how many such subsets can you form?
2 to the power 12.
2 to the power 12. But now just think about it. See, we cannot choose any subset. The way we are allowed to define a function is very particular. I mean, in your choosing this subset, suppose somebody chooses 4, 4 as well as 4, 3. Will that be a valid function? You
No.
cannot choose both of them, right? Then that will not be a function, because then what you are saying, f of 4 is equal to 4 and also f of 4 is equal to 3. That is not allowed. So there are some restrictions on how you can create the function. But think of it the other way. Just as we created the subset, right? See, I want f of A has 4 elements, right? Let's say the elements of A are 1, 2, 3, 4. And I want to assign 1 to some value. So how many choices are there to assign 1? Your B has 3 elements, right? So the first f of 1 can be defined as any one of these 3. So there are 3 possible ways to choose f of 1. What about f of 2? How many choices for f of 2?
We'll have 2 choices.
Why 2?
So because we first have originally without any restriction, it will be 3 choices. But since we've already taken one element of them, that will be f of 1. We can't have f of 1 and f of 2 mapping to the same element.
No, so that means the basic definition of the function is not clear. See, you can have a picture like this, right? F of 1 is also 1 and f of 2 is also 1. There is no problem with that. The reverse is not allowed. F of 1 taking 2 values is not allowed, but 2 elements having the same output, there is no problem with that. So you can choose f of 2 independently of f of 1. Does that make sense?
Yeah.
Okay, so then f of 2 also has 3 options. And so continuing that way, see, every element will have 3 options, right? F of 3 can also be chosen in 3 ways. F of 4 can also be chosen in 3 ways. Out of, like, it could be that all of them map to the same element, no problem. I mean, it's a very boring function where all the answers are equal to 1. F of 1 is 1, f of 2 is 1, f of 3 is 1, f of 4 is 1. So the picture will look like this. It's a very boring picture, but it's still a valid function. There is no problem with that. Okay, so then how many total functions will be able to form this way?
Three to the power 4.
3 to the power 4, right? So now just generalizing this to any two sets with size m and n, what can we say? So let's say set A has m elements, set B has n elements, and we are looking for functions which go from A to B. So how many such functions can we form?
N to the power m.
Sorry, I just relabeled them. Can you repeat your answer in terms of n and
It
k?
will be k to the power n.
K to the power n, correct? Because the first element of A can take k possible values. Second element can also take k possible values. So it's k into k into k n times. So it is k raised to n. Okay. Are others also following this? That how we are counting the total functions from first set to the second set?
Yes, sir.
Okay. So this was without any restriction. So the function can be very boring, as we said. All of them can point to only one element and things like that. But now let us count with some conditions that. So we already seen two possible conditions that f can be 1, 1. So f is 1, 1 and f is on 2. Okay. So now let us explain these terms also before we count them. Okay. So 1, 1 means what? 1, 1 means that this is not allowed. Okay. 1, 1 means that if you put it in English, basically two inputs cannot have the same output. Okay, that is a sort of crude way to put it. What is f is 1, 1? Or in more formally, if let's say f of a, f is a function going from a to b, we can say that if for any two elements a1 and a2 in a, their output should not be equal. Okay. I mean, we're assuming that a1 is not equal to a2. If a1 is not equal to a2, then their output should also be not equal. Suppose we put this condition and ask the same question again. Let's say your A has 3 elements and B has 4 elements. Then count how many 1, 1 functions are possible. Where f is 1, 1. So how many such functions can we create?
Should be 4 times 3 times 2, right?
4 times 3 times 2, correct? So this is where, I mean, what you are saying, Anushka, that once the first element has been assigned, that option is no longer available for the second element. That logic will work here, correct? So f of 1 has 4 options. It can be any one of the 4 possible values of set B. Once f of 1 has been assigned, f of 2 will be left with only 3 options because the first f of 1 is no longer available, right? And f of 3 will have 2 options. So therefore, the 3 into 2. Okay.
Yeah.
Suppose,
so in
I
this
mean,
case, the number of functions would be b factorial, like mod of b factorial.
now that depends what is the size of A and B. So let us try to do this in general terms. Let's say A has n elements, B has k elements. So then let us count in n and k.
So over here, first of all, since it's injective, we have to we have a condition that every element in A would map to different element in B.
Correct.
So the number of elements in A has to be less than equal to number of elements in B.
Correct. So n less than equal to k is a requirement. Otherwise, such a function cannot exist. That is correct.
Yeah, and then the total number of possibilities will be k factorial because the first one will have k choices, the second
Yes.
one would have k minus 1, and so on.
But where will that series end? So suppose you have set A as a number 1, 2, 3 up to n. So the first f of 1 has k choices, that I agree. F of 2 has k minus 1 choices, correct? But so where will this series end? It will end with
So
f of n.
k minus, yeah.
So the last will be k minus n plus 1, correct? So you don't actually go all the way up to 1. So it is not the product, entire product from k factorial, but only a part of that, right? So can we represent this in some way? This product.
So we can first of all write k factorial and then divided by so n minus 1 factorial.
N minus 1. Why n minus 1?
k minus n factorial.
K minus n factorial, because and if this series continued, then the terms after that will be k minus 1 all the way up to 1. And we don't want to include this part, right? So we have to divide by that.
So this will be kpn.
KPN, right? So KPN. So KPN, which is the number of ways to arrange n elements out of k elements. Yes, Raghav, you have to raise your hand.
The same thing.
Okay. Okay, so do you see this is actually like a permutation problem, because what we are saying is that we want to arrange three elements. Like if I put them in a straight line, f of 2, f of 1, f of 2, f of 3, and B has the choices 1, 2, 3, 4. So basically out of these four objects, I want to arrange them in three positions. So that is exactly the same problem we are solving. Okay. So the number of one injective functions is kpn from size n to size p. Okay, and the important condition is that this n less than equal to k has to happen, because the reverse picture will not be possible, right? If you have three elements in set A and only two elements in set B, after you assign two elements, the third one will be left with no choice. So this cannot be a injective function. Okay, so we have answered the question of how many total functions there are and how many injective functions there are. Now let us come to the surjective question. So or onto. So F is or onto or subject or surjective. If again to put in English, basically what we are trying to say is that every object in the second set gets assigned. Okay. In other words, every object in the right set, the what we call the codomain, has to have some element of the first set that gets mapped to it. So there cannot be a case where there is some element of the right hand side for which there is no corresponding object from the first set. Okay. So for example, consider this function f of n to n, where f of x is equal to x plus 1. So first question is f 11, and then is f onto.
So it will be 1 to 1. Right?
It will be 1 right?
Yeah, 1.
But is it onto?
So it won't be onto because the first element won't be mapped.
Correct.
Like if we start with 1, so it will the mapping would start from 2.
Right. Because the picture is looking something like this. This is our first set. This is our second set. So 1 is getting mapped to 2, 2 gets mapped to 3, etc. So it is 1, 1, because if x is not equal to y, then fx will also not be equal to f of y. So 1, 1 is 2, but it is not onto because there is nobody who maps to the first element, right? Yes, Ayush?
Sir, can you explain what onto means again?
Sure, sir. So I mean, actually, this example is the perfect example to explain. See, this function is not onto because there is an element on the right hand side which is not the answer to any question. So there is no element in the first set such that its answer is 1. So therefore, this function is not onto.
So if it was whole numbers to natural numbers, this function would be onto.
Yes, exactly, very much so. So if let's say you are mapping from whole numbers f of w to n and the same function definition, then it will be onto, because then what will happen? 0 will go to 1, 1 will go to 2, etc. Correct. And also if let's say the function was from all integers to all integers, you see even then it will be onto. Because there also what will happen, every element on the right hand side will have, so if y is there on the right hand side, then y minus 1 will be there on left hand side. So f of y minus 1 will be y. So therefore, so this function is both 1, 1 as well as onto. Okay, do you follow? Okay, so I mean, to make this even clearer, I would ask you to try to create a function of all the four kinds. So try to create a function right now. Let's say everybody try to define a function where first case of if is neither 1, 1 nor onto. Okay, then try to create a function which is 1, 1 but not onto. Then try to a function which is not 1, 1 but is onto, and finally a function which is both 1, 1 and onto. So let us try to come up with one example of each function. And you can choose any domain, codomain you want, doesn't matter. Okay, I'll give you a few minutes to think about this. So 1, 1 and on to.
So I think I got a function for the first case.
Yes, tell me.
Maybe x squared for it from for integers to integers.
So f goes from z to z, and f of x is equal to x squared.
X squared. So for example, minus one and one would give one,
Yes, correct.
and three won't be taken in the right side.
Correct. Right. Okay, does everybody follow this example? That this function, like pictorially, what will it look like? That -2 and +2, they are both mapping to 4. So therefore, it is not 1, 1. And there are elements on the right hand side for which there is no corresponding element on the left side. So there is no such element whose square is 3. So therefore, this function is neither 1, 1 nor onto.
Even I want an example.
Yes, correct.
So if f of x is equal to greatest integer function root x.
Greatest integer function of root x. And what is the domain of the
Yeah, so from natural numbers to natural numbers.
natural number to natural number? Okay. So I can see this is not 1, 1, but why is this not onto?
So because all elements. One second.
So this is not 1, 1 because basically if you have two numbers between perfect square, like between 4 and 9, any number you take, its answer will be the same, right? 5 and 6, for example, they will all have the same answer. So it is not 1, 1, but I think it will be onto, right? Because see, as you keep increasing x, right, sooner or later this number will take on every possible natural number.
Yeah.
So I mean, just to make this function not onto, what you can do is just change the RHS to a slightly larger set, such as all integers. Now this is guaranteed to be not onto, right? Because this answer will never be negative, and that is because this is radical of x. So radical means we always take the positive square root. Yes, so this is a valid function. Any other example? Very simple example. I mean, the most trivial example, which can be not 1, 1 or onto. Try to think of the simplest possible function, which is not 1, 1 or onto. Anybody? How about a constant function? The most boring function you can think of. Let f of any domain, doesn't matter. Let's say n to n. and f of n is equal to 1 for all n. Is
Say
this-
f of x is equal to 1 for natural to natural or natural to integer.
Do you see this? This is neither 1 1 nor onto.
Yeah.
Yeah, it's obviously not 1 1 because everybody is mapping to 1, and it's not onto because apart from 1, no other element of the second set will have any representation. Right? So basically, any kind of this as a constant function can be useful here. Okay. Next example, a function which is 1 1 but not onto. I think we just saw an example of that above it. F of n to n. F of n is n plus 1. Right? This is an example of function which is 1 1 but not onto. And maybe you can come up with few other examples also. Then what about the reverse? F is not 1 1 but it is onto. Anybody?
So I think I have one.
Yes. Tell me.
Sir, it will be same like x squared, but
Mhm.
from real numbers to positive reals.
Real numbers to positive reals. I think you have to take non-negative reals, right?
Sorry, no, non-negative.
Yeah, correct. That is a valid example. So f goes from all reals to only r plus 0. This is sometimes used to indicate non-negative reals. F of x is x squared. Yeah, I think we all can agree that this is 1 1 and this is not 1 1 because f of minus x and f of x will be equal. And it is onto because this set of non-negative reals, each element of that set will have at least one square root. So therefore, this is not 1 1 and it is onto. Correct. One more example can be exactly the same domain R to R naught and f of x is equal to mod x, absolute value of x. This will also have the same behavior, correct? Because absolute value will map all the negative values to the positive values. So every element, every positive element will have two what we call pre-image. Okay, so this is when f of a is equal to b, b is called an image of a under f, and a is called a pre-image of b. Okay, so image and pre-image. This is a common term used. Okay, so onto means basically every element has to have at least one pre-image.
Yeah, so in this function f of x is equal to mod x,
Mhm.
the domain can be integers and the codomain can be positive, non-negative integers also.
Yeah, correct. Even that is possible. So instead of reals and non-negative reals, you can take integers and positive integers, non-negative integers. So, yeah, correct. Okay, and finally, a function which is both 1 1 and onto. This is the simplest case because this is just like basically 1 to 1 correspondence. So there will
Sir,
be like countless
x.
examples of it. Sorry, Raghav?
F of x equal to x.
Yeah, correct, exactly. The identity function, okay, f of x equal to x. For any set, as long as the same set is used in both cases, it will work. Okay, so I hope with these examples, it is a bit clearer that what is the meaning of 1 1 and onto. Because I mean, I want to ensure that everybody is clear on this because these are very fundamental concepts in whole of mathematics really, like functions, sets, injective, surjective, all of these things. Okay, so then we have already answered the question of counting the one function. Now we are going to count the onto function. Okay, so suppose some set A and B are there. Okay, A has n elements, B has k elements, and we are looking at all functions such that f is onto. So how many such functions can exist? And we, as earlier Anushka pointed out, that if f is 1, then the necessary condition was that the first set has to be smaller than the second set. In the same way, for onto, do you see the reverse condition has to be true? That n has to be greater than or equal to k.
Yeah.
Because if n is less than k, we will run out of elements of A before we have covered all the elements of B, correct? So this is not allowed. And so this is the reason why if a function is 1 as well as onto, it forces that the two sets have the same number of elements, because n less than or equal to k as well as n greater than or equal to k. So that forces n is equal to k. Okay, so that is why bijection is going to create this kind of 1-to-1 correspondence. Okay, so then suppose we are given numbers n and k such that n is greater than or equal to k. Still the question remains, how do we count these onto functions? And we can start with a numerical example. So let's say n is equal to 4, mod A is 4 and mod B is 3. Okay, so you have 4 elements in the first set and 3 elements in the second set. And now do you start to see that this question is very similar to the question I asked in the problem set, because I can rewrite this problem in terms of there are 4 objects and there are 3 types, and I want to assign each object to one particular type such that every type gets covered at least once, correct? The question I asked in the problem sheet says every type is covered at least twice. I mean, boxes is just a different terminology, but so this is an even simpler question. We are not even saying that every element of the right side has to be covered twice. We just want it to be covered once.
So I think this would be 4 to the power
4 to the power
3.
No, that is the set of all functions, right? But we are not allowed to have a function. I mean, a function where everybody goes to 1, for example, is not onto. So we cannot just count the possibilities of 1, 2, 3, 4 independently. Now there is a dependency between their possible counting. Oh, sorry. You said 4 to the power 3, right? I think because you are looking at the reverse way. Like, let's say we 1 get mapped to 4 possible answers. That way, I think we're looking at it.
Yeah, I did that.
Yeah. So the problem with that logic is there is a possibility in that some element of the left hand side doesn't get covered. So I mean, let's draw the reverse angle, that 1 can be mapped to one of 4 elements. Let's say 1 gets mapped by 1. Let's say 2 also gets mapped by 1. 3 also gets mapped by 1. This picture can emerge in your counting, but this is not a function.
Yeah.
But
so but at least 2 elements of A have to map to the same element in B.
correct, that is correct. So how can we use that information to do the counting? Or just to put it in terms of how Raghav described the problem earlier. So let's say x1 is the number of elements which will map to the first one, x2 to the second one, and x3 to the third one. So what we know is x1 plus x2 plus x3 has to be equal to 4, and all of them have to be greater than or equal to 1, correct? So how many solutions are there for this equation? Do you understand the question? That x1 is the number of objects sort of A which will map to number 1, x2 for 2 and x3 for 3. So since all the objects of A have to map to one of the three, so therefore the sum of x1 plus x2 plus x3 has to be equal to 4.
6 choose 3, right?
6 choose 3. 6 choose 3 because what is 6 choose 3? The number of solutions to this equation?
Just 1 minute.
Yeah, what you're saying is correct if this condition were not given. Xi greater than equal to 1.
That is xi greater than equal to 0, right? Understood.
Right, correct.
We'll have to do x1 minus 1.
Correct. So that's the standard trick that we use, right? Let's just subtract 1, 1 from all the three elements and we'll be left, let's just call that y1, y2, y3. Okay? So
And that will be
y1
1.
is x1. So then, and here all these yi will be greater than equal to 0. So how many solutions for this?
That will be 3 choose 3. No, wait, 3 choose 2.
Yeah, so 3, right? Basically, I mean, the only possibilities are 1, 0, 0, 0, 1, 0, and 0, 0, 1. You can just count it that.
Yeah.
Okay. And so basically adding the 1 back, I mean, the first original equation also had just 2, 1, and 1, and rearrangement of this 2, 1, 1, and 1. So this is exactly what you were saying, that what does this 2 mean? That there are some 2 elements of the first set which are both going to map to 1 in the second set. So then how can we do the counting now? So suppose we are going to work with this case. So the case is where so we are expecting 2 arrows to land in on element 1, 1 arrow on the second element, 1 on the third element. So all that is left is to choose which object of A will go into which category, right? So first thing we can choose which 2 elements are going to map to 1 in 4 choose 2 ways, correct? So 4 choose 2 ways to select some 2 elements which are going to land to the first object. After that, so now we are left with two elements on the left hand side which are not used anywhere, and 2 possible targets. So how many ways are there to assign the rest of the targets? So the second target can have 2 possibilities, right? I mean, this one can come from either 2 or 4. So there are 2 possible ways for the second target, and whatever is left one has to be good, has to be mapped to the last target. So the answer is 4 choose 2 into 2 into 1, right? And this is answer actually 12. So in fact, we can even list out all the possible functions in this case. However,
Instead of counting like that, I had one more method. Like
sure.
first of all, we say that 1, 2, and 3. So one is mapped to any of the 4 elements.
Okay.
Then 2 is mapped to any other 3 elements, and 3 is mapped to any of the 2 elements. So 4 into 3 into 2. But then we have one element left which can be mapped with any of 1, 2, or 3.
Yes.
So for doing that, we'll have again 3 ways, right?
Yes.
Yeah, so that we could proceed that way and count it.
So, but what is the answer you're getting with that?
So no, I mean, we have to subtract some cases. I'm not getting how to, because here we are getting 4 into 3 into 2 into 3. So
Right.
I think
so yeah.
72.
No, yeah, exactly. So the approach which you are using, there is a possibility of double counting there. So can you explain your approach once more?
Yeah. So we start with the B set.
And just a minute, let me just do one thing. This because both sets have 1, 2, 3, 1, 2, 3. It's hard to talk about it. Let's call these ABC. Okay. Yeah. Now tell me.
So we start with set B. So we
Okay.
map A to any of the 4, 1, 2, 3, 4. So that is 4
Okay.
ways.
Okay.
Then mapping B to any of the remaining 3. That's 3 ways.
Okay.
And mapping C to remaining 2, that's 2 ways. So 4
Okay.
into 3 into 2.
Okay.
And then we have one element in A left. Say the number 4 is left. And we
Okay.
have to map it to A, B, or C. So that is 3 ways.
So the problem with this approach is, see here, what you're doing is you're forcing that the first mapping that you're doing, right? Let's say one gets mapped, one is the element which is getting mapped to A. Now, when you're considering element B, you are assuming that B will no, okay. So B will get mapped by 2, that is fine. Basically, the order, the same output can be created in 2 different ways. Let's say we do it this way. One gets assigned to A, 2 gets assigned to B, 3 gets assigned to C, and 4 also gets assigned to C. Okay, so this will be one of the cases that you will count. Now consider you will also count the same thing one more way. In your original mapping itself, it is possible that you will map C with 4, and now your remaining element is 3, and now you have to assign 3 to somebody, and let's say you end up assigning 3 to C again. So you are counting the same function twice now. The only difference is in your first round, you are assigning the element, different element, and in the second round, you are assigning a different element. But ultimately, the elements getting mapped to the C are the same. This can
So
happen,
that
right?
will be double counting. So that should be 72 by 236.
72 by 236.
Still, it's 3 times more, right?
Right. Correct. That is correct. But I mean, the difficulty is that although here the answer did come out to be correct, finding out how much double counting is happening can be very tricky. I mean, we are working with small numbers, so it was easy to spot this. But if you take larger and larger numbers, right, these possibilities of double counting keep on increasing. Okay.
Sir, but then using your method, we got the answer as 12, right?
Yeah, but yeah, by the way, that was 12 if we assume the distribution is 2, 1, 1, but there are 2 more
Okay, 3
distribution
ways to
possible.
do that.
Yeah, correct.
Right.
So basically the 2, 1, 1 case gave me 12, and the other will also give me 12 each, right? Therefore the answer is 13. So our answers are tallying for this problem. There is no problem with that, but the difficulty I perceive is that if you take general numbers m and n, right, there your approach will make it harder and harder to double count that, eliminate the double counting that. Okay? Actually, the thing is, even this approach which I am describing will very difficult to scale it up, but just to illustrate that how you can do this problem. Okay, now we are going to look at a completely different way to do this problem, and that is actually the approach which can be generalized, and that uses what we call the inclusion-exclusion principle. Okay. So, I mean, first thing, even before we apply it, I would just want to check. Can you raise your hand if you're already aware of what is this principle? Okay, Anushka, Rathod. Others, if you are not studied this, then we can quickly recap this first before we apply it. Okay. So this is just a technique that can be used to count the number of elements in a set, or either a union and intersections or different set. Okay. So basically the idea is, the simplest example we can start with is let's draw a Venn diagram of 2 sets A and B. Okay. And we are interested in counting the union of the 2 sets. Okay. So number of elements which are belonging to both either A or B. Okay. So how much is the answer of this for those who already know?
Sir, it would be number of elements in A plus number of elements in B minus the number of elements in A intersection B.
Correct. And what is the logic that we can quickly explain for this?
So like if you're looking for A union B and you take both the sets, so you take number of elements A and number of elements in B, you see that the middle portion is repeated twice.
Correct.
That's the intersection.
Right.
So you subtract it one time and then you get the fun.
Yes, correct. Okay, so basically the left hand side has to count all the elements in all the 3 regions exactly once. Okay, with this first term on the RHS mod A, this is counting the elements in everything in A once each. The mod B part is counting all the elements in B each once. So as a result, this is getting counted correctly, this is getting counted, but this is getting counted twice, 1 plus 1. So therefore, you have to subtract one copy of this intersection, which is A intersection B. Okay. So this is the sort of the simplest two set case of inclusion exclusion, but we can generalize this to n sets also. So I mean, as a first step, let us try to write the same thing for 3 sets. And now I'll give you some time for those who don't know the principle. Can you try to create the same expression now? So A, B, C, all 3 are there, and we want A union B union C. Okay. Anushka, if you know already the answer, let's just wait for a couple of minutes and others can also try. Well, I know we are spending a lot of time on only one problem, but that's okay. I mean, right now the important thing is that we study all the theory, get all the details correct before we solve too many problems. Okay, so yeah, Anushka, if you know the solution, but instead of just giving the answer, can you explain how we decide to write each step? Like, what should be the first thing we write and the second thing after that?
Yeah. So first we'll take the number of elements in A, B, and C
Correct.
without excluding anything, the total number of elements.
Correct. So with that,
Then
let me just mark like which area is getting counted how many times. So when I say mod A, I'm counting all of these ones. With mod B, I'm counting all of these ones. With mod C, I'm
So
counting
actually, you can name the points, name the regions as 1, 2, 3, 4, 5, 6, 7.
Yeah, we can name them also. That is fine. Actually, my diagram is a bit too small. Sorry, let me just redraw it slightly larger. Okay, let us name them some. Okay, 1, 2, 3, 4, 5, 6. Yes. So
Yeah.
now
So
with,
when we
yeah, go ahead, go ahead.
Okay. So when we are counting A, we are counting 1, 2, 7, 6, and 7. Then we are
Correct.
counting B, we are counting 2, 3, 4, 7. And when we
Yes.
are counting C, we are counting 4, 5, 6, 7.
Correct.
All of them. So we
Correct.
see that the regions which are there, which are like shared by exactly two of these circles, they are
Yes.
being counted twice. So we
Correct.
need to subtract those regions. So that is B intersection A. So A
Correct.
intersection B, B intersection C, and C intersection A.
Correct.
So we subtract those. Yeah.
Right. So now with that, we have removed some of the double counting. So which of the
we have removed 6, 2, and 4 once, and we have also removed 7 thrice, because in each of the 3 we have the 7 region. So we have removed all 3 of them of 7. So we have to count the 7 region once.
correct, correct.
So now for that we'll have to add in A intersection B intersection C.
Correct. Okay. So unfortunately I erased the marks, but basically this region had basically this region was getting counted twice, once from A, once from B. So to discount that, we had this term minus A cross B. So that out of the 2 ones, one of the ones will go away. And the same for the others. But in the process, we first added the region 7 3 times and then we subtracted the region 7 3 times. So we were ending up with region 7 having 0 count. So we need to include that again, and so to the add that +1, we added this. Okay, so I hope this pattern is clear for others also. I mean, you can work it out similarly for slightly larger set also, A, B, C, D, and see how it works. But the way the terms are written also, there is a clear pattern there, right? First we add all the elements of set size 1, then we subtract of size 2, and then we add of size 3, etc. So with this motivation, at least we can write the expression of the general case, even though we have not proven it. Let's say we have set A1, A2 all the way up to AN. So then the union of A1 union A2 union AN, this can be written as the sum of first all the single element single sets, their modulus. Then we have to subtract all the intersections of two of the sets, AI intersection AJ, where I less than J. Then we add all the three set intersections. Like this. So the most general term will be -1 raised to k. So k is the number of sets that you are considering. Sigma of I1 less than I2 less than Ik. So we are supposed to choose k distinct indices and the intersection of AI1, AI2 all the way up to AIK. Okay? And I mean the last term of this will be all the n sets will be represented. Okay, so this is what we call principle of inclusion and exclusion. And do you see where that name is also coming from? Because what we are doing is we are alternately including some regions, then excluding them to overcompensate, sort of compensate the double counting. Then again we have to include some regions to overcompensate, etc. So that alternate inclusion and exclusion is what's happening. Okay, so this is a very powerful technique for counting a union of sets, provided that these intersections can be easily counted. So if these intersections can be counted, then that can be used to count the union. Okay, and there are many examples of this which can be given. So I think I covered this very systematically in last year's lecture. So I can point you to whichever lecture will cover all the examples, which I otherwise I will not do all of that right now. But just to illustrate this, so our problem of onto function counting is a perfect case to use this technique. Okay? So before we do that, just one small sort of modification can be done here. So here we are counting the union of all these sets, right? So this is the region inside this Venn diagram. But I was always drawing a box outside that, which is the universal set. Okay. So in some cases, we are interested in not counting the union, but the complement of the union, which is all this area. Okay. So all the elements which don't belong to even one set. Okay. So suppose I have to count this outer region, all I have to do is subtract the union from the entire count, right? So if I want to count this outer region, all I have to do is S minus this whole product, the sum rather. So that will be given the sum of this outer region. So when I do the subtraction of all of this, just the sign will flip. So the initially what was it, the initial first element was positive, second was negative. With the reverse, it will be the first element will be negative, second will be positive, and so on. Okay, so sometimes that version is more useful, and sometimes the union part is more useful. Okay. So with all of this information, let us turn back to our own original onto problem. So again, set A has 4 elements, set B has 3 elements. So now the first challenge is we have to construct this set A1, A2, etc. So let us try to construct them in this way. So let S1 be the set of all functions such that, and by the way, let us again use, in fact, let me use PQR, not even ABC, because small a, capital A, confusion I don't want. Such that P has no pre-image. Okay. So what does that mean? There is no element in set A which is getting mapped to point P. Okay, let all such functions go in the set S. Okay, similarly, let us define S2 and S3 with for Q and R. Okay, so S1 is the set of all elements where P is not getting mapped. S2 for Q and S3 for R. and let S be the set of all such functions without, so S is the universal set, okay? All functions A and B without any other additional condition. Okay. So our Venn diagram looks something like this. Okay. S is our universal set which has all the functions, and we already know what is modulo S, right? How many functions S has? Is 3 raised to 4, correct? Because every element of A will have 3 choices. So 3 into 3 into 3, 4 times. So this is the universal set, and inside that set, we are considering these 3 S1, S2, and S3. And we are interested in counting the onto function. So onto means that in fact the reverse of each condition has to be true, right? So we want a function where P has also pre-image, Q also, and R also. So which region in our diagram do we want to count for onto functions? We want to count the region which is outside all the 3 sets, right? We want to count the complement of that really. So what we are interested in counting is this exterior region, because this will contain all our onto functions. Does that make sense? Okay. Is this clear, or you want me to give any examples? For example, let us take some example of a function. I mean, same set 1, 2, 3, 4. Let me define the function and you tell me which set it will belong to and which set it will not belong to. So let us say F1 is P, F2 is P, F3 is Q, and F4 is also Q. So which of the 3 sets S1, S2, S3 will this function belong? So will it belong to S1?
Yes, sir.
See, the condition of S1 is that we want all functions where P does not have any pre-image, but F1 is equal to P. So it means that there exists an element whose image is P. So F will not belong to S1, right? The fact that P is occurring on the right hand side, which means that F is not satisfying the condition of S1.
So, can you repeat what is S1 again is?
S1 is all functions F going from A to B where the first element, the what I said P, right, has no pre-image.
Oh, okay, yeah, that one be this.
Right? So which of the 3 sets will this function belong?
It'll be S2.
S3.
Why S2?
Because there, no. It will just be the complement of S1, right? Because it's not in S1, so.
No, see, S1 and S2 are not complements of each other, right?
It's like, no, not S2, it's like complement of S1.
Yeah, it will belong to a complement of S1, but will it belong to S2? So S2 says we are looking at all functions such that Q has no pre-image. So if your function is taking the value Q anywhere, it means that will not belong to S2.
Yes.
Right? But here F3 is equal to Q. So therefore, F does not belong to S1. F also does not belong to S2. Does it belong to S3?
You say it can belong to S3 because there's no R.
Yeah, there is no R, right? So F will belong to S3. So therefore, in our Venn diagram, this function will lie in this region, correct? Outside S1 and S2, but inside S3.
Yes.
And this is clearly not onto, right? Because it is not mapping R anywhere. So in that sense, now you understand that a function which is outside all S1, S2, S3, that is an onto function, because that function will take P, Q, R, all the values will be represented. Okay, is that clear?
Yes.
So this is the area we want to count, the outer part. Okay, and we, as I said, that we can use inclusion exclusion principle to do that. So this region, if I denote it by some variable x, okay, so I want to count mod of x. Okay, so that will be equal to, if I write out the whole expression, it will be universal set minus, first we add all the single element sets, not ABC, sorry, S1, S2. Then we subtract the two intersections. And finally, we add the sum. So this is the count of this red region that we are interested in. So now the only question is, can we count each of these individual regions? If we can count them, then we can find the answer. So mod of S we have already answered, that is 3 raised to 4. And now we have to answer all the other questions. But note that S1, S2, S3 will be symmetric, right? So if we find the answer of one of them, that will be give us the answer of the others. And similarly, S1 intersection S2, once we count that, we don't need to separately count the other two cases, because that is just cyclically they will be similar. And what about S1 intersection S2 intersection S3? How many elements will this set have? See, S1 intersection S2 intersection S3 is a function which does not map P, Q, or R. None of them get mapped. So that cannot happen, right? Because when you define the function, we have to assign each of the elements, f of 1, f of 2, f of 3, f of 4 has to be assigned to one of the three P, Q, R. So you cannot have that all the three images are not taken. So therefore, basically this number is 0. So basically this middle portion is empty. So actually our diagram should be looking something like this. So this is S1, this is S2, and maybe S3 is something like this, right? So there is no part where all the three are intersecting. That is what the diagram should actually look like. But that's very hard to draw, so we just draw it in the way I draw here, and understand that the middle intersection of all three has to be empty.
So we could draw a circle that is touching the point where the two.
Yeah, we could draw it that way, maybe like this and something like this, if possible. Yeah, but anyway, I mean the diagram is just a representation, but do you understand the logic why the intersection of all three will be empty? Okay, so now the only thing left is we have to count S1 and count S1 intersection S2. Okay, so let us first try to count S1. So S1 means the only condition on the function is that we should not use a point P. So how many elements S1 will have?
Q or R.
Q or R. So, but like how many functions will be there in S1 which satisfy that condition? So to count such a function, right? If A has 4 elements, 1, 2, 3, 4. So I need to assign F1 some value, F2 some value, F3 some value, and F4 some value. And the choices I have are Q and R, right? So there are 2 choices for the first one, 2 choices for the second one, and 2 for each of 3 and 4. Q or R, Q or R. And they can be equal. So there's nothing stopping. We are not talking about 1 function here. It's purely onto. So all of them can be Q, all of them can be R, or some combination of them. But total, how many such functions will be able to form?
2 to the power 4.
2 to the power 4, 16, correct? So mod of S1 is 16. And whatever is the answer of S1, S2 and S3 will have the same answer, because it is, instead of P, we are just considering Q or R. So mod of S1 has 16 answer, or 16 possible. What about S1 intersection S2? So S1 intersection S2 means we are looking at a function which does not use P and also does not use Q. So how many such functions can we create?
1.
Only one, right? Because we are forcing all the values to be equal to R. So therefore, now we know how much is the count of each of these intersections. So can we write the answer of capital X now? So it will be 3 raised to 4 minus. So all of these can be grouped into 3 times 16, or let me write it as 2 raised to 4. Plus all of these can be grouped as 3 times 1 raised to 4 minus 0. So how much is this coming to be? Yes, it is coming to be. Is it coming 36?
Yes.
Okay, so it is matching the answer that we got earlier. Okay, I hope this method is clear to everybody, because probably this is the first time many of you are getting introduced to inclusion exclusion principle. So I understand this can be hard to follow. So I will encourage you to go and watch my previous last year's lecture on inclusion exclusion. I spent, I think, one full lecture, or even maybe 2-3 lectures on just this topic, where we also look at the proof of the formula. I mean, here we just observed the pattern and directly wrote the formula for n sets, but we need to prove that. So I'll encourage you to do that on your own, or take help from my previous lecture. But this is a good example of how this technique can be applied. And importantly, this complementation idea is very useful. See, actually, you would have thought that why are we defining set S1, S2, S3 like this? Like S1 is the condition that P is not getting used, whereas we are interested in onto function, where onto means we want P to be used, right? But here we are using the defining S1 in the reverse way, the complement, and S2 and S3 in the same way, because what that allows us to do is consider the region outside all of S1, S2, S3, and that is the one which we want to count. Okay, you can try to see what happens if you took the reverse condition. If you first count all functions where P gets used, okay, that is actually harder to count than the complement. Okay, so you can try to generalize this for a larger set now. That suppose A has some n elements, B has k elements, and of course given n greater than or equal to k. Now how many onto functions are there from n to k? Okay, so I will encourage you to try and solve this problem on your own, and then once you do that, then you can look at the question which I had asked. This given 3 types of objects, whatever the number of ways to place one object in 8 distinct boxes, because this is even harder question than the previous one, because here not only we are saying that every type has to be counted once, we are saying it has to be counted at least twice. So this is an even harder way to solve the problem, harder problem to solve. Sorry. However, that is using inclusion exclusion principle, but practically, if you are faced with this problem in IOQM, you don't need to know so much theory. So let us do this problem without invoking all of this theory, because it can be done in a very simple way also. Okay, so this is how we can do this problem. Given three types of objects. So basically, let us label the objects A, B, C, D, E, F, G. Okay. And we have three types. So type 1, type 2, and type 3. So very simply, just as what earlier we had done, Raghav, right? Let x1 be the number of objects which take type 1, x2 is the number of objects which take type 2, and x3 number of objects which take type 3. So x1 plus x2 plus x3 will be equal to 8, right?
Yes.
And not only that, we know that each of these has to be at least 2. So how many solutions do you have for this
So
system?
you write y1 plus y2 plus y3 is equal to
Yeah, so Anushka, I would suggest not to do that, because we are trying to answer how many solutions we have, but we are actually interested in listing out all the solutions. So just purely by trial and error, can you list the solutions?
so we can have 2, 2, 2, 4,
Correct.
2, 3, 3.
Yes. That's all. And rest will be just permutations of these,
Yeah.
right?
Yeah.
So there are only two possible ways to distribute. So 2 to 4 means that, well, let me not label the objects A, B, C, D, E, F, G, but let me label the position. So let's say the first, let's say we are counting 2 to 4. So let's say x1 has 2, x2 has 2, and x3 has 4. So there are two positions A, B available here, C, D available here, and E, F, G, H available. So how many ways are there to choose the A, B? So A and B can be chosen in 8 choose 2 ways, right? Out of the
Yes.
eight objects that were available, any two can be assigned x1.
So
So
what
now
will just be the multimodal coefficient? Like 8 and 2 to 4.
yes, yeah, correct. That what we call the binomial coefficient, correct. But I don't know what is the convention to write that, so I'm just writing it out explicitly.
Oh,
So yeah, but it will turn out to be the same value. That I agree. So basically, it choose 2 for assigning the first elements. Now we are left with 6 objects, and out of those 6, we have to choose some 2 for C and D, right? So 6 choose 2, and the remaining 4 choose 4 will be forced into the last bucket. But this is for 2 to 4, and we have to consider permutations of 2 to 4, right? 2, 4, 2, and 4, 2, 2. So this
yes,
whole thing will have to be multiplied by 3. And the same for the other case. So if you have 2, 3, 3, then it will be 8 choose 2, 6 choose 3, and 3 choose 3. And again 2, 3, 3 can be permuted 3 times. So into 3. So just adding all of this will give me the answer that I'm interested in. So this is like the most straightforward way to solve this problem. Okay, does everybody follow this? So let's actually find the answer, by the way. So 28 into 3. So that makes a mistake. Yeah, so this has to be 20.
Two nine four zero.
Okay, and that was n, and the question is asking find the number of sum of the digits of n. So, but the answer is 2940. Okay, so I hope this method is clear to everybody. So this is the clean and simple way to do this problem. And I mean, the only reason why this is doable is because the numbers are small. But if I give you slightly larger numbers, then you have to use something like inclusion exclusion principle. Okay. But now let's do this problem using inclusion exclusion. I know we have already spent a lot of time, but let's just complete that because we are already reached there. So how can you formulate this problem in terms of inclusion exclusion? So there are three types of objects, right? So I can write my inclusion exclusion in this way, that let the universal set be the number of ways to assign the objects without any condition. Okay, so number of ways, not number of ways, actually the number of ways, there is distribution without any conditions. Okay. So S is all possible distributions of the how many 8 objects into 3 boxes, right? So what will be the size of S?
So 3 to the 8.
Yes. Okay. Now let S1 with the number of distributions such that type 1. So the question is asking us to count such that each type is represented at least twice. So our set will be the complement of that. So type 1 is taken at most once. Okay. S2 will be the same. S2 will be the number of distributions such that type 2 is taken at most once. And S3 is the set of the elements where type 3 is taken at most once. Okay, so this at most once is the part which is adding the complement in the problem. Okay, and I think the Venn diagram will look very similar to the previous case. So what we are interested in is the complement of, we want to count S1 union S2 union S3 whole complement, because we want all cases where at least type 1 is taken at least twice, type 2 is taken at least twice, and type 3 is also taken at least. So this will be nothing but the universal set minus the same product. So sigma S1 plus sigma S1 intersection S2 and minus sigma S1 intersection S2 intersection S2. And I can replace the sigma by the number 3 because we know that the symmetry it will be that way. So here we already know this, the answer of this is 3 raised to 8. So we just need to find S1 intersection S2 and S1 intersection S2 intersection S2. So again, do you see S1 intersection S2 intersection S3 will be empty because we have 8 objects. So we cannot take each type at most once. That will simply not work. We will not be able to distribute all the objects. So S1 intersection S2 intersection S3 is again 0, right? What about S1 and S1 intersection S2? So how much is S1?
So it would be 15, right?
How much?
No, so one second. I think I made it.
So condition of S1 is that type 1 is taken at most once. So we have considered 2 cases, right? So case 1, we don't use type 1 at all. Okay, so type 1 is not used at all. And case 2, where exactly one element, exactly one object is of type 1. So in the first case, if we, let's say we don't use type 1 at all, then how many possibilities are there?
So 9 possibilities, right?
Wait, I think I made a mistake here.
So because if x1 plus x2 plus x3 is 8 and x1 is 0, then you get x2 plus x3 is 8.
No, but again, you are making the mistake of assuming they are identical objects. I mean, the boxes are distinct, right?
Oh, yeah. Yes.
So it will be the same as what we did earlier for onto, right?
2 raised to 8.
2 raised to 8, right? Because each object has 2 choices, either it is of type 2 or type 3. The answer of this will be 2 raised to 8. And in the case 2, where exactly one object is of type 1, what will happen?
8 into 2 raised to 7.
8 into 2 raised to 7, because we have 8 choices to choose which that object will be, which will be forced to be type 1. And for all the other 7 objects, we have 2 choices. So the answer of mod S1 is 2 raised to 8 plus 8 times 2 raised to 7. Okay. What about S1 intersection S2? So now S1 intersection S2 will have 4 cases, right? Because we can say that how many objects of type 1 are there and how many objects of type 2 are there. So we'll have 4 possible combinations, that maybe there is not a single object of either type. Maybe there is one object of type 2, one object of type 1, and one object of both types. So in each case, we'll get an answer. So suppose we decide not to use type 1 or type 2, then what will be the case?
1.
Only one possible copy.
Only, let's say only one object of type 2, then
Eight.
It would be 8 possibly.
8, right? Because we just have to choose which that object is, and all the other objects are forced to be type 3. Here also 8, and in the final bucket,
8 to 6.
8,
No, 2 into 8 to 6.
2, yeah, or 8, you can just say 8 into 7, 56, right?
Yes.
Because basically 8 choices for a type 1 and 7 choices for type 2.
Yes.
And everybody else will be forced to type 3. So now we know all the answers. So can we compute this answer and see if it tallies with our previous approach? This entire inclusion exclusion expression. So the answer should be equal to 3 raised to 8 minus 3 times mod of S1. So 2 raised to 8 plus 8 times 2 plus 3 times mod of S1 intersection S2. So by the way, this sum is equal to 56 plus 17. 73. And S1 intersection S2 intersection S3 is anyway 0. So we can ignore that.
But so this will be a lot of calculation.
This will be a lot of calculation. Yeah, I'm not recommending this approach, but I just want to illustrate how we are getting the same answer with this approach. Yeah, I'm also getting to 940 in this case also. Okay, so you see we are getting
Yes.
the same answer. So I mean that is expected, but it's good to have confirmation that such a complicated method is giving the same answer as our original method. So probability is really good that both our approaches are correct. Okay. So yeah, I mean I hope that with this example it is clear how you can do the same problem by making explicit cases like this, or doing the way that we did below. So depending on the sort of complexity of the problem, you can choose which approach is feasible. Okay, this was question 1. Then question 2.
So I was not able to solve question 2,
Okay.
but then I have some idea, but I can't go ahead there. Like the only
Sure.
the only things I get is that the sum of the integers has to be minus k, And the product
Yes.
has to be 8 times k minus 12.
Right. Okay.
I am not sure how to go beyond.
Okay. So, I mean, the solution which I have in mind, just to give a hint to how to approach that. See, first thing to observe is that here the way it is given, right? This is a typical trick that the paper setter will use to make it look complicated, where every term has a part of k inside it. So, as a first step, let's try to rearrange the terms in a way where we take all the part which is independent of k to one side and all the part which has k in it. So, let's just first rewrite it that way and see if that gives us some useful information. So the expression is x4 plus k x cube minus 3x square minus 5 minus 2x times 3x plus 10 plus 8 times what k minus 4. This is my original polynomial, right? Let us call this p of it. Okay, so as I suggested, what happens if we just take out the part which has k, and what will the polynomial look like after that? Okay, so let's first write the part which does not have k. So that will be x raised to 4 plus 15x square minus 20x minus 96. And what will the rest of the part? And note that you can now take k common out of everything else, right? So now you can write k times what will go inside the bracket. Okay, so this is our polynomial p of x. Do you agree?
Yes, sir.
Okay, so now I want to pay close attention to this part, which is inside the bracket. It's a cubic, so we cannot directly solve it like we have that formula, but it's too complicated to apply. But just by pure observation, can you guess one root for this part?
So one thing is, I think that will be k times minus x cube. No, I think it's minus k times the thing you've written.
Why is that required?
Okay, you've not taken it to the other side.
No, we're not taking it to the side. I'm keeping everything onto one side. I'm just rewriting the polynomial in this way. So, what can you say about the part inside the bracket?
Sir, 1 is a root.
1 is a root because, I mean, just the pure observation, note that 1 plus 8 is 9 and minus 3 minus 6 is 9. So, 1 is clearly a root. So, can we factorize this?
Yes.
Okay, so what are the factors? So, 1 being a root in x minus 1 will be one factor. And what will be the other two factors?
Sir, x minus 4 and x plus 2.
X minus 4 and x plus 2. Okay, so which means our polynomial can be written as the first part plus k times this. Okay, and we are interested to find the roots of this polynomial. Can we at least find the value of this polynomial in a few places? Do you observe that because of this factorization, which means that for at least these 3 points, the value of k does not matter at all. you see P of 1 can be computed no matter what case. P of 1 will always have some constant value. Because this part will become 0, the right part, right? So
Yes,
which
sir.
value can be computed this way?
1, 4 and -2.
1, 4 and negative. So let's do that. So what is P of -2? P of 1 and P of 4. Can you compute and tell me? Actually, you know what? I am not even interested in the value. But observe something about these three quantities. Like if I try to draw a graph of this polynomial, what will it start to look like now? So we are computing it at -2, 1 and 4.
So you're talking about only k times that part of the whole polynomial?
Whole polynomial itself. I mean, k times this part will be 0, right? At these three
Yeah.
values.
Yeah.
So that allows us to compute P of x. I feel I made a mistake somewhere. Either in copying the problem from my notes or I have a feeling I made a mistake somewhere actually. Okay, but anyway, can you find so how much is P of 1? P of 1 is 1 plus 15 minus 20 minus 96. I mean, value doesn't matter, it's some large negative value, correct? That is
Yeah.
P of
Yes,
1.
sir.
What about P of 4? You see,
Positive.
it's
It
going to
will
be
be
a positive value. So then what does that tell us?
Uh,
The
And we are
root
interested.
lies between 1
Yeah.
and 4.
Exactly. And we are also given that all the roots are integers. So only possible values are 2 and 3. And I think I made mistake because even -2 was a positive value. So but here actually it's not turning out to be the case. So I might have made some small sign error. -2 is not positive, right? Because actually it's -96 will dominate everything. So I think I made a mistake somewhere. But anyway, that was the intention at least, that this was going to be positive. So there is one root in this region and one root in this region. And then from that, I mean, there's just a finitely number of cases that you can try out. And actually, it's obvious that 0 cannot be a root because no, it's not obvious that way. But you can work it out, the cases basically. The only possibilities are one of these two has to be a root and one of 2 and 3 have to be a root. That is forced. And from that, you can compute the rest. Okay, but is the approach clear that how we are able to arrive at this? Important thing was to observe in the original expression which part depends on k and which part does not depend on k. And like this separating in like if you ask me in one phrase, what is the theme of this problem? This separation of variables. Okay. You separate K from everything else and then you see the relation of that. Okay, is the idea clear for this question?
Yes, sir.
Okay, yeah. I mean, I'm not completing it here because anyway, I think there is some sign mistake. So I'll fix the problem in the worksheet and you can attempt it again. But in any case, this was the approach. So you see how simple this problem is really in a way, because there is no advanced theory we are using. Just regrouping the terms and observation is all that is helping us. And actually, I created this problem by literally changing a few values in one. So here it is x raised to 4, right? I think RMO 2018, my problem, the exam RMO 2018 question paper had the exact same idea with just cubic instead of quadratic. So quartic, but the idea was exactly the same. Okay, question 3. So find the number of ordered pairs such that some conditions, and the main condition is this one, that psi of mn is equal to psi of m into psi of n. So we need to think about how can we use that. So psi of mn, psi of n is defined as n minus phi of n. There phi is of course the Euler function. I did mention that. So psi of m into psi of n will be if I expand this, it will be and psi of mn will be mn minus phi of n phi of n. And we are given the condition that these two are equal. So therefore, what will we get? Mn will cancel and we'll get m phi n plus n phi n equal to twice phi of n phi of n. Okay. So after arriving at this point, can seem that we are a bit lost, because if you think about it more carefully, I mean, obviously we have things such as, we can see phi of m is there in both places. So this has to divide this part. So phi of m divides m times phi of n. But that doesn't seem to be very useful at the outset, because particularly the formula for phi of m is a bit clumsy. I mean, it has it depends on which prime numbers are occurring. That p1 raised to k1, p2 raised to k2. Those will come in the denominator and it's a bit messy. So this doesn't seem to give any clear idea about how to proceed.
Then maybe we can try to factor it in terms of phi of n and phi of m. Like, if we have variables x and y, so it will be like mx plus ny is equal to 2xy, something like that.
Okay.
Equal to 2xy. And then I am not quite sure how.
Yeah, I mean, I can certainly understand the motivation that x, y, and xy are all present. So some regrouping can be done. Actually, not a bad idea to think about. So, for example, if let's say you want to force the factorization on the left hand side, let's just add xy to both sides. So we'll get mx plus ny plus xy is equal to 3xy, and then to complete the factorization, we should also have mn.
Mn.
So what we'll get after rearranging is m plus x times n plus y is equal to 3xy plus mn. But after that also, I mean, doesn't seem to be very helpful directly. M plus x divides 3xy plus mn is not, it's not easy to process that. Okay, but so this is where actually focusing on this red equation once more, want to bring to your attention one more important aspect which I always highlight about number theory problems. See, there are two sides of the coin. Divisibility is one coin, estimation is the second part. So in general, just in terms of magnitude, right? And let's say without loss of generality, m less than equal to n. Okay. What can you say about phi of m and m magnitude wise? obviously phi of m has to be smaller than, in fact, strictly smaller than m. Not strictly, because it can be 1, but okay, let's at least less than or equal to m, correct?
Yes, sir.
Or can you say something even stronger? So particularly the ratio phi of m upon m is less than or equal to 1 is what we can see here. But now knowing the formula for phi of m, right? Now if I assume the factorization of m as p1 raised to k1, p2 raised to k2, let's say pr raised to kr. So then we can write phi of m upon m as it will be just those 1 minus 1 by p1, like p1 minus 1 by p1, p2 minus 1 by p2. Those kind of terms will be there. Okay, and notice how each of these terms are, they're almost equal to 1, very close to 1, right? So for example, if we are taking some small prime factors like 2 into 3, 4 into 5, 6 into 7, this kind of product, very basic product, right? So I mean, at first one suspicion is that this product of numbers which are very close to 1, how less can this will be almost equal to 1, but turns out that's not the case. If you just multiply these three factors, right, 2 by 3, 4 by 5, 6 by 7, their product is just below half. Okay, so seems like, and if you keep adding more terms, you can make this ratio as small as possible. So I think in general phi of m upon m can go all the way to 0 also, maybe, quite possibly. But this is where actually the problem helps us, because problem is telling that m and n are actually very small numbers, less than 20. So that puts a natural upper bound on how many such fractions we are going to be able to multiply. In fact, we cannot even have 3, 5, 7 all together, because it means the number has divisible by 3, divisible by 5, and divisible by 7. So that is already 105. So in fact, 3 terms like this also cannot be present. So with some observation, you'll realize that at least for the range given to us, right, m less than 20, phi of m upon m cannot be even less than half. Okay, this has to be greater than half only. Okay, because what will happen, even if let's say your number has two prime factors, 3 and 5, so 2 by 3 into 4 by 5, this product is also greater than half. And if you have only single prime factor like 7, 11, 13, doesn't matter which prime factor you take, that ratio is obviously greater than half. So no matter what you do, phi of m by m will be greater than half. And same for n also, by the way. So what is the implication of this on the red equation? So that red equation, let me just rewrite it here. So m phi of n plus n phi of m is equal to 2 times phi m phi n.
So now we can maybe divide both sides by phi of n, phi of m.
Yes, correct. So with that, what we'll get is m upon phi of m plus n upon phi of n is equal to 2. And now do you see that this is basically impossible, because
Yes, sir.
I mean, because half is less than phi of m, which means that basically m upon phi of m. Yeah, actually, I would like to divide by mn, but it's okay. So m upon phi of m is greater than, strictly greater than half, or strictly greater than 2 actually. So this both terms are greater than 2, so that sum cannot be equal to.
Yes, like, or we can just say that since m is greater than phi of m,
Hmm.
greater than or equal to phi of m, so which
Oh,
means
yes.
the sum is greater than or equal to 2, which means m and n have to be 1.
Yeah, correct. So that is the only solution. If m and n are not equal to 1, then this will be strict inequalities, one of them. So the equality cannot happen. So m and n is equal to 1, 1 is the only solution. So the answer of this problem is that oh, interesting. So I guess in your solution we don't even require this condition, right? We didn't use this at
Yes,
all.
sir.
So interesting. I didn't observe that. Yeah, in fact, that's a very nice solution then. Yeah. So I hope others followed what Raghav explained, that this original equation gets divided by phi of n, and we'll get m upon phi of m plus n upon phi of n equal to 2. And now these both ratios will be greater than equal to 1, right? Because m will always be greater than phi of m. The only exception being if both m and n are equal to 1. So therefore, that is the only possible answer. And we don't even require to use this condition, which I thought that we had to restrict the fraction or something. Okay. So you see, this kind of question is a combination of some algebra and some observation of the terms, that how big can a term be or how small. Just pure observation of those kinds can be used to solve a problem like this. Okay. So with that, we can move on to question 4. Anybody who has solved question 4? Question 4 is actually very interesting, and actually, if more people were joining, they would benefit from that theory. But anyways, for those who are present, there is a lot of interesting implications of question 4 which we can discuss, and quite surprising also in some ways. But note that you can do this problem using simple pure geometry also, not using any of the theory which I am talking about. Okay. And just to give me a minute, I'm trying to think what is the best way to start explaining this problem. So, and maybe I'll talk about the pure geometry approach first to motivate, forgetting the advanced theory. How are you supposed to do this problem in an exam? So, whenever the question says that PQ passes through a fixed point, there is so much vagueness, right? The question is not helping you at all. It just says some fixed point in the plane. It can be any point. And if you don't have any clue which point you're supposed to prove that PQ passes through that point, you cannot solve the question at all. So first thing is we need to somehow find what is that fixed point. And then once we have located that point, then we can try to prove something that okay, PQ passes through that. So that location of that fixed point is important. And unless we know that, we cannot make any progress. Right. So you can maybe without any other prompting, maybe you could try to do something like just try to take various values of OP and OQ and see what's happening. Right. So basically, if you take P and Q somewhere like this, and we are saying that PQ has to pass through some fixed point, okay, some point R. We don't know where this R is, and even if the position of P and Q change, it will still pass through the same point. That is our claim. So, and what is the condition given to us is that alpha upon OP plus beta upon OQ is equal to gamma. So can you think of how I can try to estimate the position of this fixed point? You are given a lot of freedom. You can choose P and Q anyhow you want. But which value of P and Q will be really helpful for us?
Then maybe 1 and 1 or alpha or something like that.
1 or alpha, but I mean that pair has to satisfy the condition, right?
Yes, no, like if you take OP to be 1,
Okay.
then we get alpha plus beta by OQ is equal to gamma.
Yes.
Or if we
correct.
take OP to be alpha, we get beta by OQ is equal to gamma minus 1.
Right. Yeah. Yeah, we can try to do something like that. So let's say if we choose OP such that this distance is 1, then we'll get some equation and that will fix the position of Q for this. We can call this pair P1 and Q1. And in another case, let's take a point Q2 such that this distance is 1. That will fix the point P2. And wherever these lines intersect, P1 intersects P1 Q1 and P2 Q2, wherever they intersect, that will be the position of R. Right?
Yes,
But yeah, this can be done, but the calculations can be still kind of messy because this is not really helping us to define the position of R while avoiding all the calculations. This like intersecting two lines can be non-trivial. What else can we do? What else can we do? So just trying to draw the picture, like intuitively, like if we just keep on drawing various positions of P and Q. Is there any upper bound on how far we can take the point P or Q? Does that give any intuition about what can be done?
So there's no upper bound, right? Because it can go forever.
Exactly. So then, I mean, assuming that there is some fixed point R, we don't know where it is, but assuming that there is some fixed point R, and we construct it this way, we just, let's say you choose point Q anywhere you want on the line, doesn't matter where, and wherever QR passes through, it will give me some position of P, right? And let's say we keep pushing Q farther and farther. What will start to happen? What will start happening to this line itself? In the
It will
limiting case,
some sense become like parallel, I guess.
exactly, it will start to be more and more parallel to this line, right? Do you see that? And I mean, we cannot actually put it to infinity, but as it becomes closer and closer to infinity, this line will start to become more and more parallel. And so, in that case, even P will start to come somewhere over here. So this PR line will start to be more and more parallel with the base, right? And in terms of this expression, what will happen to OQ? See, OQ is
One
becoming
upon also would come as small as 0, right?
exactly. So effectively, you can ignore this term, right? This is almost as good as 0. So in the limiting case, you say I can find the position of P where for that point this Q will go to infinity. So basically what I'll get is OP is equal to, and let me give you that point some special name, P star. Okay. So OP star will be equal to alpha by gamma, correct? And can I do the same thing in the other direction? Instead of pushing point Q to the infinite location, I can push point P to an infinite location. So as point P keeps going farther and farther, this line PR, wherever it intersects Q, this RQ will become more and more parallel to this other ray. So in a way, I can define the special position of, like if I draw this parallel line, this will be Q star. So I know OQ star also, right? OQ star will be beta by gamma, because in that case, the first term will be very close to 0. So now do you see how I can construct the position of this point R?
Yes,
We are
sir.
still guessing, we are not sure, but at least we have a good guess for how we can construct R now, right? So we can locate the points P star and Q star because alpha, beta, gamma are known constant. And then we can complete that parallelogram, right? So we take P star such that this distance is alpha by gamma. And we take Q star such that this distance is beta by gamma. And if we complete that parallelogram, at least intuitively seems to be a reasonable claim that this is that fixed point that we're interested in. Okay, do you agree?
Yes, sir.
Okay. So, I mean, this is a useful way of how you can use what is called extremal principle. Okay, extremal principle. Like you deliberately try to take the values which are very small or very large and try to estimate what is going to happen. And that gives you some intuition about what you can do. So, I mean, this is a really good progress that we have found that potential candidate. And now the problem is to prove that no matter what PQ you choose, those PQR are going to be collinear. So now in the real problem, I mean, P and Q will not be at infinity, but they will have some fixed finite positions. But now given such points P and Q and such a point R, now we want to try and prove that PQR are collinear. So let me give you some time to think and see if you can solve the problem now. But you know, so this is exactly how INMO problems are often. Actually, this problem is a bit easier for INMO. And anyway, this cannot be asked in INMO because this is kind of a standard property, but the problem, the solution thought process is what I'm trying to illustrate. Don't try to use something complicated or fancy like trigonometry or anything else. I mean, I'm not saying don't think of that also, but first think of simple ideas and then think of advanced ideas. Because many problems like this can be solved using simple ideas also. I mean, nothing that I've discussed so far is beyond even school geometry, to be honest. So now given that, so far by beta by gamma, prove that okay. So first thing we should try to do is eliminate alpha, beta, gamma from our consideration because they are just acting like an intermediary to connect the points P, Q, R together. So we know point R can be defined in terms of P star and Q star, right? And writing P star and Q star is difficult every time. So let me just write them maybe capital A and capital B. It's okay. Okay. So we know that OA is alpha by gamma and OB is beta by gamma. So we can just substitute that in our expression and eliminate alpha, beta, gamma completely, right? So let's say we divide by gamma first. So we'll get alpha by gamma upon OP plus beta by gamma upon OQ is equal to 1. And now alpha by gamma is OA. So basically what we are given is OA upon OP plus OB upon OQ is equal to 1. Then prove that PR, QR collinear, where R is the point which completes the parallelogram AOBR, right? So given that AOBR AOARB is a parallelogram. Okay. So you see how we are keeping on rewriting the question until we can simplify it as much as possible. So now even alpha, beta, gamma are not required. All I'm given is that there is a parallelogram and some points P and Q such that OA upon OP plus OB upon OQ is equal to 1. And I have to prove that PRQR collinear. And it's not very hard for you to see that this is going to be an if and only if condition. So in fact, any line passing through R, if it intersects the two rays in points P and Q, they are going to satisfy this equation. So this is going to be if and only if. Okay, so continue simplifying the problem. This R being the fourth vertex of that parallelogram is a very complicated description of that point. So can we simplify that description and consider the midpoint of OA? Okay. So the midpoint of OR and AB, which is the same point, right? I mean, basically, let's apply homotheity to the whole diagram with ratio half and center as O. Okay, so that R will go to this point, R dash. And if PRQ are collinear, then the image will also remain collinear, right? So P will go to P dash and Q will go to Q dash, but P dash, R dash, Q will also be collinear. And OP dash is nothing but OP by 2. Okay. So what I'm suggesting is one more round of rewriting the problem. So now I don't even want the point R. I just want AB at the midpoint of AB, and I, instead of calling it R dash, let me call it S. Okay. And given points, again P dash and Q dash is a clumsy notation, so let me just refer to them as P and Q. So now what is given is OA upon so here OP was twice OP dash, right? So here I have to write twice OP plus OB upon twice OP is equal to 1. Given this, prove that PQ passes through the midpoint of S, midpoint of AB. So now basically we have a triangle with 3 points, one on each side of the triangle. So what do we really require? You see, it's enough to show just converse of Menelau's theorem. If I prove that OP upon PA into AS upon SB into PQ upon QO is equal to -1. Or I mean, if you forget the sign and just look at the magnitude. If I prove this, am I done?
Yes, sir.
So all that we can hope is that this condition and the given information are equivalent. And I will now not check that, but I think they should turn out to be equivalent. It will be very disappointing if they are not. And out of that, AS upon SB is simply 1 because S is the midpoint, right? So this is 1. So if OP upon PA is equal to OQ upon QP, if we can prove this from this information, then we are done. And I mean, the only change is that this has OA and OB, whereas this does not have OA and OB. But like introducing those terms should be relatively straightforward.
And just maybe subtract 1 from both sides to get O and OP, maybe.
Yeah, exactly. And I think there has to be some consideration about the convention because we don't know whether P is going to be inside or outside A. Like what is the order of the points on the 2 segments, we don't know. Actually, it's not hard to show that if P and Q are both inside, right? You cannot have a picture like this where P, Q are both on the same side because then what will happen? Both of these ratios, their sum will be greater than 1. So therefore, we necessarily require a picture where 1 point is outside and 1 point is inside. So I think without loss of generality, you can consider this picture. And then now we can write OA as OP minus AP. So just rephrasing this term. And now OB will be OQ plus QB. And now I think from both sides, 1 copy of half will come out. Right? So this will be half minus AP upon twice OP plus half plus QB upon twice OQ is equal to 1. And so this half plus half will cancel with the RHS and you will get exactly this term. Correct?
Yes, sir.
Yeah. Okay. So this was the pure geometry approach, and it involved a lot of steps, but understand all the steps were just simplification, how we replaced each problem with a simpler version of the problem. And we kept simplifying until the final part was so easy that one Menelau's theorem could finish it off. So this approach of repeated simplification is an important problem solving technique. And you should apply it as much as possible just to reduce the complexity. So in fact, the starting point was we didn't even know where this point R is going to lie. So the first thing was to guess what that fixed point is. For that, we use extremal principle. Then having guessed the point, we saw an opportunity to get rid of alpha, beta, gamma as first step. So that everything is in terms of OP star and OQ star. Then from that also we found that, so always the idea is of what we can call independent information and derived information. So in this problem, at this stage, like OA and OB were independent fundamental variables, and everything else is derived in terms of that. So R is derived in terms of OA and OB. And the description of R was very complicated, like the parallelogram completed by OA, AOB. So we simplified that description, and to do that, we considered the midpoint. So now instead of talking about the parallelogram, we are just talking about the midpoint, right? S. So here still OA and OB are the independent variables, and S is the dependent object. So we cannot get rid of the dependent object completely, but we simplify the description of that object, and then the problem can be solved.
So how did we get like if P prime and Q prime are, and R prime are collinear, then PRQ is collinear?
By homotherapy, right? Because if PRQ are collinear and P dash R dash Q dash are the homotherapy of those with ratio half.
Sir, I don't know what's homotherapy.
Oh, sorry. Homotherapy is just you must have done this in 9-point circle. I thought that
Actually, I'm an 8th grade, so
is there a different name for that which you use?
so 9-point circle we study in 8th, but it's in the end.
Oh, okay, sorry. Okay, then let me just talk about homotherapy quickly. This is actually a whole topic called geometric transformations, which we should study at some point. But basically, homotherapy is a dilation of an object.
Right.
So basically, it's an operation where you choose some point O in the plane and some ratio, some real value k. And if you have any one object in the plane, like let's say some S set, then you take every point of your set and you just change it to a new point P dash, so that OP dash upon OP is that constant ratio k. So you can imagine that like blowing up a balloon, right? If you have a small object, you just magnify that through a lens and you'll get a larger copy of the same object. So that
Okay, so it's literally similarity.
it's similarity, exactly. It's similarity with some ratio. And so therefore, in the original set, if you have 3 collinear points, they will remain collinear under this operation, right?
Okay, sir. Yes, I got it. Thank you.
So here the ratio is half. So by ratio half, we so that k can be greater than 1 or less than 1. Greater than 1 means we are magnifying, and less than 1 means we are diminishing. I don't know what the reverse name. So this PRQ with ratio half will become P dash R dash Q dash.
Yes.
Yeah. So when you study 9-point circle, you will learn that the 9-point circle and the circumcircle are homothetic versions of each other through the orthocenter and the circumcenter.
Okay.
And in fact, there are a lot of, homothetic is a very simple idea, but it is, you'll see it everywhere. Even so, have you done in-circle and ex-circle configuration?
Yes, sir.
Yeah. So there also do you see that in-circle and ex-circles are homothetic versions of each other, because the in-circle is here and ex-circle is somewhere over here. So with the suitable ratio through the point A, do you see that I can transform this smaller circle into the bigger circle?
Oh, okay, sir.
Everything of the in-circle will get mapped 1-to-1 with the ex-circle. And you can see that the ratio of homotheticity I need to apply is R1 upon R, correct?
Yes.
Yeah. So in a way, it's a good thing that you are not introduced to this. Now you can try to apply this wherever possible and see how many different homotheties you can spot in different configurations which you already know.
Okay.
Okay.
Thank you.
Okay, so this was the pure geometric approach to this problem, but I want to just talk about something very interesting which can be done, which is motivated by this problem. So I hope we know some basics of coordinate geometry. Like just what is coordinate geometry? It is like in a plane, every
Yes.
point can be assigned an x and y coordinate. Okay, just a very simplest possible view of the theory without going into too many details. And the way we imagine that is that if we draw perpendiculars on the x and y axis, then this is what we call the x coordinate, and this is what we call the y coordinate, right?
Yes.
So every point in the plane can be given this kind of two like are two real variables are enough to describe every point in the plane. Okay, so this is what we call Cartesian system or Cartesian coordinates, because it was created by Descartes, one of the famous mathematicians. And turns out that this is only one way of assigning two real numbers to every point. You can come up with your own new coordinate system. In fact, there are many varieties. So there is one thing which is called polar coordinates. In polar coordinates, the two numbers we describe are not the x and y like altitudes, but instead of that, you use the distance from the origin. So like the distance r and this angle theta. So r and theta, this pair is also a pair of real numbers. And this is also useful. This can be used to describe any point in the plane in the same way, right? And we have a convention like theta going counterclockwise is positive. So for example, if I give you the coordinates 1,45 degrees, then you know exactly which point I'm talking about. That I need to look at the ray which is angled at 45 degrees, and I need to travel a distance of 1. Okay, so this is the point which has polar coordinates 1,45. And it's easy to see that the same point can also be described in Cartesian coordinates as 1 by root 2, 1 by root 2.
Sine theta, cos theta.
Sin theta and cos theta. So
Sorry, cos theta, sin theta.
cos theta, sin theta. So you see there are multiple ways to assign coordinates to the points in the plane. And depending on which system you use, like the standard objects like line, circle will have different equations. So like in standard Cartesian coordinates, can you tell me what will be the typical equation of a line, like some general line? What will be the format of that equation for a line?
Ax plus by.
Like
equal
ax plus
to
by is some constant, x plus by to c kind of equation, right? And what will the circle look like? Some circle.
X square plus y square equal to r.
Yeah. Okay. Let's take a circle centered at the origin for simplicity. So that will be simply x square plus y square equal to r square. And now you see in the polar coordinates, a circle is so easy to describe. So if you are talking about
Just be
circle,
r.
yeah, exactly. So r is equal to t, is a circle of radius t. So some systems make some objects easy to describe, and in polar coordinates the line will be kind of harder to describe. Okay?
Yes.
So that kind of interplays there. But apart from these two systems, I mean, these are not the only two systems you can use. You can use a completely new equation. So here we took the x and y axis as perpendicular to each other, right? But let's say I want to choose an angular axis, okay? Axes which are not perpendicular to each other. Okay? So this is my x axis and this is my y axis. And now any point in the plane, I need to give you a method of how to assign coordinates. So instead of dropping perpendiculars, I complete the parallelogram. So basically, you see this is direct generalization of the 90-degree system, because in a 90-degree system, when we draw perpendiculars, we are actually completing the rectangle. But here we are completing the parallelogram. And again, same as before, this distance is what I call the x coordinate, and this distance is what I call the y coordinate. And under this system also, do you see that every point in the plane will get a two real numbers to describe that point?
Yes.
Okay. And now, I mean, this is the part where either you can sort of intuitively see that, or if you want, you can prove it also, that under this system also, any line has the same equation, ax plus by equal to c. Not the same, but similar looking equation, that some x coordinate and some y coordinate equal to c. Okay, it has a very similar format. Okay? This is, I mean, I'm just giving this information to you, but with some little intuition and algebra geometry, you can prove this also. It's not very hard. Okay. So the fact is that under this system of description also, a line remains like a linear expression. Okay? And this is not by accident. Like in 11th and 12th standard, when you study linear algebra and matrices, you will see there is a deep connection between this system and our normal like 90-degree system. Okay, there is like if I give you a point in this system, like if I give the coordinates at x, y, and I want to describe the same point in a different system, and if I call those coordinates x dash, y dash, then what are the equations that relate the original coordinates to the new coordinates? So what is the system of equation that relates xy to h dash y dash? That is what the matrices are. Okay, so whenever you study matrices, you will deal with all of this in a big way. But right now, what is important to us is just to note that a line has the same looking equation ax plus b by equal to c. Okay, so with this background in mind, now do you see that our problem, right? What we were given, right? See, we were given that OP and OQ points and some equation of alpha by OP plus beta by OQ is equal to some gamma. So with some work, we can actually see that this basically OP and OQ we are describing are the coordinates of some point, right? I mean, whatever is the value of OP and value of OQ, they are going to uniquely define a point in the plane. So that is the sort of very different way of looking at this problem. Anyway, I won't talk more about this because I mean getting into calculations is a bit pointless right now. But just to give you a different way of looking at things, that the 2D coordinate system of what we know is just one example, and you can do something very similar in a completely different frame of reference. Okay. But yeah, I mean, I don't want to talk more about that right now. Okay, so actually we don't have enough time to cover question 5 and 6 today. In fact, let me skip question 5. It can be done in actually kind of elementary problem in many ways actually. Somebody has already solved or tried question 5 and like completed it. Okay, if not, then let it be, because you can, I think it's easy enough that you can attempt it on your own and hopefully I think you can get it. But if not, we'll discuss on next class. But let me talk about question 6 a bit more, because that is a completely different style of questions called functional equation, which we have never dealt with before. So it's a whole theory in itself and needs to have a dedicated lecture actually. But just to introduce what is the concept of a functional equation and how we are supposed to get started with a problem like this at all. So a functional equation is an equation where the unknown variable is not a value, but it's a function itself. Okay? So the question is telling you to find a function which has a certain property. Okay? So for example, whatever that question was. So the unknown variable is not some x or y. The function f is itself the unknown variable. Okay? So you are supposed to find a function here, let's say q plus 2q plus, which satisfies some property. So in a way, now that we understand what is a function, so for every rational number in the given range, right? So I want to find f of q. And as such, there is no restriction on the function being nice. Okay, there is no condition that f of q has to be a nice polynomial or formula or sine of x or cos of it. It can be completely wild function. Okay, there is nobody is going to make a commitment to us that you are always going to deal with nice functions. So in that sense, actually every real rational number can have a completely different value. Okay, it can be completely chaotic. So f of 1, f of 2, f of 3. I cannot even list down every possible pair, f of p of q. Each of them can be given a completely different value, which has no connection with any other value. Like under no, if like no condition is given. So the space of such functions that can be drawn, like if I try to plot a graph of the function, you may think that the graph may look like some nice value, but it can be some very, very crazy. It cannot go like this. This is not allowed because then it means that a single value has two y coordinates. So that is not allowed. But apart from that, the function can look something like this also. It doesn't even have to be continuous. It can have like bits and pieces which have different graphs, or the graph cannot be drawn also. Like there are some really crazy functions where the graph looks like this. So it's like I cannot even draw it on the paper. But all of these are valid functions, and we don't know if our given problem, the solution is one of such crazy functions or not. Okay. So in general, this is a very hard problem because in a way, I'm not asking you to find the answer of one variable or two variables. I'm asking you to find the value of infinitely many variables. What is f of 1? What is f of 2? What is f of 3? What is f of 1947 upon 2022? Each of these can have a different value. But so this is where the information given is going to help us, that For example, what is the first condition given? F of x, f of y equal to f of xy plus f of x upon. So f of x, f of y plus f of. So like taking some sensible number, like if I take x equal to 2 and y equal to 3. So f of 2, f of 3 is equal to f of 6 plus f of 2 by 3. So we can choose these all of these independently as long as this equation is satisfied. So and these xy values, see, you are given a lot of freedom. The question says for every x and y in the domain, this equation is satisfied. So functional equation is nothing but simultaneous equations where you are given infinite equations and infinite unknown variables. Okay, you are given infinite equations because x and y can be any value you want. Okay, so as such, you have infinite information available to us. Every value of x and y you put, you are going to get one equation. But the challenge is you have to find infinitely many values also. So, like this domain is infinite. So it is just, you can think of it like simultaneous equations on steroids. That you are not doing two equations, two variables, three equations, three variables. You are doing infinite equations with infinite variables. That is what functional equation is in a nutshell. So this is looks like almost impossible task, that how are you going to approach this? So the best analogy I can give to this, like a detective novel, like Sherlock Holmes or any such novel, that you are given clues about this function and you have to use those clues to identify some properties of that function. And to your help, you have to choose x and y cleverly. Just because you can put any value in x and y will not be helpful. So what values should you try to put in x and y? Where is
Sir,
some useful
1,
information?
1.
1, 1, yes, correct. So what happens if I put
After that, we get f of 1 is equal to 2.
correct? So if I put 1, 1, I get f of 1 is f of 1 plus f of 1. And so therefore what I get is f of 1 square is twice f of 1. And since the domain is given to be positive, so I can safely cancel f of 1 and get f of 1 is equal to 2. So that's really a good starting point, that we got f of 1 is equal to 2. So as soon as you get information like this, you have to put that to some good use. So how can you leverage this information now?
Sir, we can take x equal to x and y is equal to 1. And then we get that f of x is equal to f of 1 by x for all x when y is 1.
Correct. So if I put y equal to 1 in this equation, now I get f of x, f of 1 is equal to f of x plus f of x by 1. No, that's not very useful, right? This is going to give me the same thing once more.
Sorry, sir. Opposite.
Correct.
Yes.
F of 1, f of y. So let us put x equal to 1. So we'll get f of 1, f of y is equal to f of y plus f of 1 by y. And now since we know f of 1 is 2, so this is 2 f of y equal to f of y plus f of 1 by y. And f of y is equal to f of 1 by y. So this is again very useful information. So it means that in a way we are only going to require to know values greater than 1. Then the reciprocal is already known, right? So this is again very useful information. So like that, we have to keep finding more and more clues about what can we say about this function. Okay, anything else that we can say? See, once we know f of 1 is 2, you have to think about which of these terms can I make equal to 1, and each of them should give me some information. So we tried to make x equal to 1, we tried to make y equal to 1.
Sir, x equal to y?
X equal to y, correct. What will x equal to y give me?
F of x squared
Yes. So f of x whole square equal to f of
x squared plus 2.
f of plus 2. Correct. So this is also useful because what this tells me is that, and you have to look at it in terms of dependency. See, what this tells me is the first equation is that if I know f of y, from that I know how to go to 1 by y. Similarly, from this equation, do you know, see, if I know x, I can go to x square. So that should be useful in some way. Okay. And so far we have only used the first condition. We didn't even look at the second condition. But just from the first condition also we are able to get so much information, right? And we can keep trying small experiments like that. But now let us pause and think about the equation itself. That see the nature of that function, the nature of the information given, right? You see, it is purely like multiplicative in the sense, if I know x or y or any such f of x, f of y, I can multiply and divide by some constant term. But there is no room for addition. Like you see that purely from equation 1, if I know f of 2 and f of 3, there is no way to reach f of 5. Do you understand that? Because f of 5, the introduction of the new prime factor 5 cannot be achieved by just multiplying and dividing 2 and 3 no matter how many times you do it. Correct? You might probably, if you are really clever, you might get the answer of f of any 2 raised to k and 3 raised to alpha. This might be doable by just multiplying and dividing by 2 and 3 using some clever tricks. But there is no way to suddenly introduce 5 in that expression. So that is where fundamentally this first term is going to limit us, first equation. So to reach something like 5 from 2 and 3, we will require help from the second equation. Right? So how can you put the second equation to some good use now?
So maybe x equal to 2.
Okay, x equal to 2. What does that give us?
Then we get 2 plus 3 times f of 3 is equal to 4 times f of 4 plus 2.
Okay, let me write that. So x minus 1 f of x plus 1.
So isn't it f of x minus 1?
Oh, yes, sorry. 2 times x plus.
Of x plus 2.
Okay, so now here you're going to put x equal to 2. So we'll get
3 times f of
F
3
of-
is equal to 4 times f of
Times
2.
f of
sorry, can we do that slowly? So the first term will be 1 times f of 1, right? So this is 2
So it is
plus
3
2
times
plus
f of 3
is equal
is
to
equal to 4 times f of 4.
4 of f of 2
f of
plus
2.
So sorry, f of 2.
right? So yeah, so we'll get 3 times f of 3 is equal to 4 times f of 2. Okay.
And then
So now you see we have rated f2 to f3. That's a really good thing. From the information that we already found, if you know f of 2, what else can you relate it to? From these two,
f of 1 by 2
correct,
and
and
f of 4.
f of 4. So you see the first equation gives us a way to go from f of 2 to f of 4. Suppose the second equation gives you one more way to reach f of 2 from f of 4. Then you'll have two equations and two unknowns. So do you see how to achieve that now?
sir, x equal to 3.
Exactly. So the first application related f of 2 with f of 3. The second application will relate f of 3 and f of 4, right? So with x equal to 3, what will we get?
2 times f of 2
2 times f of 2 plus,
plus 4 times f of 4
okay,
is equal to 6 times f of 3 plus
plus
2. We can divide the whole
now,
equation by 2.
yeah, we can eliminate f3 from both these equations. So this can be written as 8 f of 2 plus 2. Okay. So then simplifying, what will we get?
2 times f of 4 is equal to 3 times f of 2 plus 1.
Let me do that one step at a time. So first this and this will get cancelled and then 6 f of 2. And then one copy of 2 will get. So 2 f of 2 is equal to 3 f of 2. Oh, sorry, 2 f of 4.
F of 4 plus
So we
1.
have one equation where f of 4 and f of 2 are both occurring. And from the previous property, can we write one more equation where f of
Yes.
4 and f of 2 are both occurring? So what will
So
that
it will be plus 1, right? It's not plus 2.
plus 1, yes, sorry. Okay. And so what is the other equation we can write from this property, right? If we put x equal to 2 here, what will we get?
F of 2 bracket square, f of 2 squared is equal to f of 4 plus 2.
So now using these two equations, can we find the value of f of 2 and f of 4?
So yes, sir. We can multiply both sides of second equation by 2
Okay.
and substitute the values.
Yeah. Yeah, if we just multiply and just add it up, then 2f of 4 will get cancelled from both sides. And for every time running, f of 2 can be tedious. So let's say f of 2 is equal to k. Okay. So the equation becomes 2k square is equal to 3k plus
Okay.
5.
Fine.
So
So we get 2k and k.
Sir, 5 by 2.
5 by 2. So f of 2 is 5 by 2.
Yes, sir, 5 by 2.
And
Another
now,
solution would be minus 1, but that is not possible.
yeah, there should be minus 1, or the negative root is not possible. So you can say f of 2 is 1. So you see how this is really like a detective novel that we found one clue. Okay, f of 2 is 5 by 2. We already knew f of 1 is 2. Can you make a guess what this function could be? Maybe try one more. Now you can find f of 3 also, right? From this equation. We can find f of 3
So
and
10 by 3.
10 by 3.
F of
And what
3
is
is
it?
10 by 3.
And f of 4?
And f of 4 would be 15 by 2 plus 1, which is 17 by 4.
So are you getting a intuition what f of x could be in general? This is like your scholarship exam paper. Complete the pattern.
Yes, sir. It is n square plus 1 by n.
Correct. Or other way to write is x plus 1 by x.
Yes.
And you see, as soon as you look at this expression, it's obvious why f of x has to be equal to f of 1 by x, right? So everything seems to be falling in place now that f of x is very likely to be this answer, but this is just a guess. We are not true on it. But I think I'll end the lecture for now. That now, given this guess, how will you try to prove this? And we have to find it for all positive rationals. So it's a big task that to prove that this is the answer for every positive rational. But try to work out it step by step, and if you can complete the problem on your own, that is really good. Okay. But
Sir,
I
but
mean,
then
yeah, tell me.
how to show that there are no other such functions?
We don't know that, but all we have shown is that we have to prove that. So if I prove conclusively that for all rationals, I can through my calculations force that f of q is actually equal to q plus 1 by q. Then that forces that is the only possible solution, right? See, if we substitute this in my expression and check it that it's satisfying, that only means that this is one solution, but that doesn't guarantee some other function cannot exist. But through calculation, if you are able to compute f of q, then there is no ambiguity, right? Okay, does that make sense?
You can find like a recurrence relation or something.
Sure, we can try to find a recurrence relation for maybe integers, but how are you supposed to reach every rational number with the recurrence relation?
No.
But think about it, you are on the right track, so I don't want to reveal the answer just yet. Okay, but yeah, I mean the functional equation is a really interesting topic, and there is sort of no upper bound to how difficult these can get, to be honest. But we have to start somewhere. So yeah, this is a good problem for that. Okay, I think that's all for now. Thank you.
Thank you, sir.
Bye,
Bye,
sir.
sir.
Thank you, sir.
Thank you. Bye.